Hi everyone. We're now going to talk about point estimates for population parameters. If a single value is used to estimate a population parameter, we call that value a point estimate for that parameter. So for example, if I were to ask you, what was the average or mean number of Netflix videos watched last week by an American adult, if you consider the population of all American adults, perhaps those who own Netflix? You might say 100 videos. I didn't say it was accurate, but that could be your point estimate for the mean number of Netflix videos watched last week by American adults who have Netflix. All right. Now, instead of just guessing, let's say that we draw a sample from a population. Well, what would make sense? It would make sense that based on these sample statistics, we're going to infer the values of these population parameters. So we use sample statistics to estimate population parameters. We will use the sample mean, x bar, as a point estimate for the population mean, mu. And this would make sense. So let's say you actually took a random sample of 800 random American adults who have Netflix. And you ask each of them, how many videos did you watch last week on Netflix? Maybe you actually get a sample mean of 100 videos. I'd be a bit surprised. Maybe not that surprising, but let's say that the sample mean was in fact 100 videos. Then that would be your best point estimate for the population mean, mu. Likewise, we will use the sample standard deviation, S, as a point estimate for the population standard deviation, sigma. So perhaps more than anything else, you have to remember what these notations stand for. The sample standard deviation is used to estimate the population standard deviation. We're inferring the value of sigma based on the value of S. And likewise, we will use the sample variance, S squared, as a point estimate for the population variance, sigma squared. So these sample statistics will typically be used as point estimates for these population parameters. So let's review these principles. All right. Example 1. A large lecture class takes a test. 5 of the tests are randomly selected and graded. The grader reports that the sample mean is 75 points, the sample standard deviation is 15 points, and the sample variance is 225 square points. So x bar is 75 points, S is 15 points, and S squared is 225 square points. I know that's a weird unit. Well, what would be a good point estimate for the population mean of test scores for the entire class? What's a point estimate for the population standard deviation of test scores for the entire class? And what's a point estimate for the population variance of test scores for the entire class after all the tests are eventually graded? Well, it would make sense that our best point estimate for mu will be x bar, 75 points. It makes sense that the best point estimate for sigma, the population standard deviation, would be S, 15 points. And our best point estimate for the population variance, sigma squared, would be S squared, 225 square points. So again, we're going to use the sample statistics as our best point estimates for these population parameters. So to quickly review, the point estimate for the population mean is the sample mean, x bar, or 75 points. The best point estimate for the population standard deviation is the sample standard deviation, S, or 15 points. And the best point estimate for the population variance is the sample variance, S squared, or 225 square points. Again, x bar is our best estimate for mu, S is our best estimate for sigma, S squared is our best estimate for sigma squared. All right. And why is it that the sample mean is the best point estimate for the population mean, or one of the reasons? Well, because it turns out that the sample mean is an unbiased estimator for the population mean. Here's a bit of theory. Don't freak out too much about it. A sample statistic is an unbiased estimator for a population parameter, such as mu, when the expected value of the sample statistic, like x bar, the sample mean, is the value of the population parameter, mu, the population mean. So again, a key reason why we use the sample mean as a point estimate for the population mean is that the sample mean is an unbiased estimator for the population mean. So in short, although you need to understand the theory behind this to understand this, E of x bar equals mu. The expected value of x bar as a random variable is mu, the population mean. Now, what does that mean? What does this signify? All right, well, consider a class, okay? So let's say here's a big lecture hall of 1,000 students. Consider all possible samples of size 5 from the class. Now, of course, this sample could be spread out at various points throughout the class, but just for convenience, let's say that one sample of size 5 looks like that. Let's say another sample of size 5 looks like that. Let's say another sample of size 5 looks like that. Remember that these samples will overlap when you consider all possible samples of size 5. So if you consider the sample mean you get from this sample of 5 students, you consider the sample mean from this sample of 5 students, you consider the sample mean from this sample of 5 students. You get these various values for x bar. If you consider all of the sample means from all possible samples of size 5, and if you line them all up and take their average, the average for those sample means, the expected value of the sample means, will be mu, the actual population mean test score for the overall class. So that means that this sample mean as a point estimate for the population mean is an unbiased estimator, meaning that unbiased estimators, like the sample mean for the population mean, they do not have a tendency to overestimate or underestimate the population parameter. They tend to target that parameter. X bar tends to target mu. There's no tendency for it to waver on the low side or the high side. There's no bias. X bar tends to target mu. And that's very helpful. Now, in general, or more generally, it turns out that, yes, X bar is an unbiased estimator for mu. S squared is an unbiased estimator for sigma squared. It actually turns out that S is technically not an unbiased estimator for sigma, but it's typically good enough, especially for large sample sizes. Things are better when the sample size is bigger. All right, so we've talked about population parameters, the sample statistics we use as point estimates for those population parameters, and also the reason why we like some of these sample statistics as our best point estimates. It helps for them to be unbiased. S isn't quite an unbiased estimator for sigma, but it's close enough. Next, we're going to talk about the population parameter P, which represents a population proportion or probability, and its corresponding point estimate, P hat, a sample proportion. That's for next time.